Alright, so in this video we're going to talk about the extreme value theorem. So this is kind of related to critical points and mins and maxes and all that stuff we've been talking about in the last few videos. So here, the extreme value theorem says if f of x is a continuous function on the interval from a to b, then f of x has a global minimum and a global maximum on the interval from a to b. So what's really important here is that f of x has to be a continuous function, and this interval from a to b has to be closed, which means both endpoints are included, and it has to be a bounded interval. So a and b are finite numbers. So in other words, it can't be an interval that goes off to infinity or anything like that. So you can have closed intervals that are not bounded, but those won't work for the extreme value theorem. The interval has to be closed and bounded. So let's make a note of that here. So this has to be closed and bounded. Okay, so basically what this says is if you have a function that just continuously moves from x equals a to x equals b, then that function automatically has to have a global minimum and a global maximum on this interval. So we'd like to see why this is true, but unfortunately a real proof of this requires some pretty advanced math, and we don't want to get into that, and we would have to take a lot of things for granted anyway, and that's not really something we want to do here. So what we'll do instead is the next best thing, which is just to build up some intuition with a lot of pictures and examples. So again, we're not really going to do a proof here, but we're just going to see some pictures and examples of why this might be true. So we'll do a few examples where we have a continuous function on a closed and bounded interval, and we'll see that those do indeed have global minimums and global maximums. So let's take a look at a picture here. Alright, so here's our x-axis, y-axis. Let's say a is here, right, and we'll start the function off here. So we'll go up for a little bit, come back down, and then go back up to here. And then here is b. Okay, so here's a, here's b. So notice the function, which we'll call y equals f of x. This function does move continuously from a to b, and this interval, it's closed, right, because it's defined at a, it's defined at b, and it's bounded because it's, it doesn't go outside off to infinity or anything. So what we have is a continuous function defined on a closed and bounded interval from a to b. So the extreme value theorem tells us this function has to have a global minimum and a global maximum. And if we look at the graph here, we see that that actually is true, right? Here is a global minimum, or here's the global minimum, I guess we should say, because it's the smallest y value out of all the y values on the graph. And here's our global maximum. Okay. So remember, global mins and global maxes can happen at the endpoints, but local mins and local maxes can't. So the extreme value theorem, it's really a theorem about global mins and global maxes on this interval here. So here's our global or absolute min, here's our global or absolute max. All right. So it's a continuous function on a closed and bounded interval. So let's see another function like that. Let's get rid of this here. So we'll see another function that satisfies all three of these conditions. So the conditions are continuous function, closed interval, bounded interval. So all three of those things have to be true in order to guarantee that the function has a global min and a global max. Okay, so let's draw another function. Let's say we start up here, and let's just go straight down this way. Okay. So again, it's a continuous function. The function moves continuously from a to b. There's no breaks, no holes, no jumps, nothing like that, no vertical asymptotes, nothing crazy. It's continuous, and it's still a closed and bounded interval, because closed because it's defined at a and b, bounded, it doesn't shoot off to infinity. So let's see what's happening here. Well, the extreme value theorem guarantees that because f is continuous and we are on a closed and bounded interval, then the extreme value theorem guarantees f has a global min and global max. And if we look at the graph, we do actually see here, here's our global max, okay, it's the highest point on the graph, here's the global min, the lowest point on the graph, right? So global max right here at x equals a, and global min right here at x equals b. So that's just another small example there. Let's do one more example with this, and then we'll start playing around with these conditions here, and we'll see what happens if the function is not continuous, or if the interval is not closed, or if the interval is not bounded. Okay, so remember, all three of these things have to be true together, but if just one of them is not true, then you just don't know what could happen. So we'll see a lot of examples with that, and hopefully that'll help build some intuition as to why all three of these things have to be true. So one more example, let's move a over to the other side of the y-axis. for no reason, I guess. So we'll put a over here. So let's put the function up here, and then it's just going to go straight across like this. Okay, so again, it's a continuous function. Okay, it's just a flat horizontal line segment, so it's continuous, no breaks, holes, jumps, gaps, anything like that. And it's defined from x equals a to x equals b. Okay, closed and bounded interval. So the extreme value theorem guarantees that f has a global min and a global max. So if we look at this here, well, you know, if you're just glancing at it, it might not look like there's a min or a max. But remember, for the definition for global or absolute min and global and absolute max, remember the inequalities, they weren't strict, right? So to be a global min, you have to be less than or equal to all the other y values. To be a global max, you have to be greater than or equal to all the other y values. But all the y values here, they're equal, right? It's just a horizontal line, so all the y values are the same. So actually every point here is a global min, and every point is a global max. So including the endpoints, right? So every single point for a less than or equal to x less than or equal to b, we have a global min and a global max at that point. So that's a third example here of a function that satisfies all three of these conditions, and then the extreme value theorem guarantees we have a global min and a global max. So let's start playing around with these conditions here. So first, let's get rid of this here and make some room. First, let's ask ourselves, what if the interval isn't closed? Okay, so remember, f of x has to be a continuous function, the interval has to be closed, and the interval has to be bounded. So what if the interval isn't closed? So we'll still have a continuous function, the interval will still be bounded, but now it won't be closed. Okay, so that means we're going to take off one or both of the endpoints, so then it won't be a closed interval anymore. Okay, so let's just have an example here. So example 1, let's say we have f of x equals the function 2x. All right, so we just have a simple linear function 2x. So part A, let's have part A over here. All right, so for part A, let's do the closed interval for part A. So we'll see another example of how a continuous function on the closed and bounded interval is going to work. So we'll draw that here. So this is going to be horribly not to scale, like almost everything I draw. So 1, 2, and then when x is 1, f of x is 2 times 1, which is 2. And then when x is 2, f of x is 2 times 2, which is 4. So we'll put 4 up here. Okay, so if we're on the closed interval from 1 to 2, then that's this point here up to this point here. So it's just connected by a line segment. So again, very much not to scale, but that's really okay for what we're doing, I guess. Okay, so here, continuous function, closed and bounded interval. Here is the global min, and here is the global max, right? So everything's okay here. Now, what if we start messing around with this interval? What if we make it so that, let's do part B. And in part B, let's say from 1 to 2, and now we exclude 1. So this is no longer a closed interval because we don't have 1 in there anymore. So let's see a picture of what that would look like. Let's try and make this one a little more to scale. So x-axis, y-axis. So 1, 2, and then 2, I guess, would be here, and then 4 would be up here. A little better, I guess. So it's going to have the same shape, you know, it's just still a straight line segment, but now because we took 1 out of the interval, we have an open circle here. Everything else is still the same though. So notice what happened. We lost our minimum value. Okay, we don't have a global min anymore, right? So we still have our global max up here at 2, 4. Okay, this is the point 2, 4. We still have our global max, but now because the interval isn't closed, we've lost our guarantee from the extreme value theorem. Okay, so these conditions, they're not satisfied anymore. The interval's not closed, so we can't guarantee this anymore. And actually, as it turns out, we lost the global min. So you might be thinking, well, what about the number that's right next to x equals 1? Won't we have a global min there? And no, the thing with the real numbers is there is no number that's next to 1. So you can get as close to 1 as you want, but no matter how close you get, you can always get a little bit closer. All right, so for example, think about like 1.1, kind of close to 1, right? But you can still get closer. So let's say 1.01. That's closer still. And then 1.001, closer still. 1.0001, that's still a little closer, 1.00001. Okay, so do you see the pattern forming here? So we can keep doing this forever and ever, right? And we'll be getting closer and closer to 1, but we'll never actually get to 1. Okay, so we can just keep putting as many zeros as we want here, but this number is never going to equal 1 exactly. So the point I'm trying to make here is that you can get closer and closer to 1, and no matter how close you get, you can always get closer still, which means you'll have smaller y values. So as x gets closer to 1, the y values get smaller, closer to 2, but they don't have an absolute minimum, because no matter how small of a y value you get, you can always find a smaller one above 2. Okay, so it's kind of a crazy property of the real numbers. Don't think too much about it, it might give you a headache. It is pretty interesting, but it's just something worth mentioning. So part C, what if we get rid of 2 and we keep 1? So we'll keep 1. Let's keep the color the same at least. So we'll keep 1, and we'll get rid of 2 now. Okay, so if we do that, the graph is going to be pretty much the same. So here's 1, here's 2, x-axis, y-axis, here's 2 and 4, kind of. So now we're going to keep 1, all right, so we still have this point here, but now because we took out 2, we have an open circle up here, right? So now look what happened. We have our global min, but now, because we don't have a closed interval still, then we lost our guarantee from the extreme value theorem. Okay, so the extreme value theorem says that if we have a continuous function on a closed and bounded interval, then we're guaranteed a global min and a global max. But we don't have a closed interval anymore, so we lost that guarantee. And actually, as it turns out, we lost our global max here. Okay, so there's no global max value here. Oops, but we do have a global min here, right? Now, just like in part B, you might be thinking, well, what about the number right next to 2? Isn't there a global max there? And no, for the same reason as in part B, there is no number that's right next to 2, no real number that's right next to 2. So, no matter how close you get to 2, you can still get a little bit closer. So like 1.9, pretty close to 2, but you can tack on another 9 and get closer, another 9 and get closer, 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 and so on and so forth. So you can keep doing that as much as you want. Okay, so then you might be thinking, okay, well, what about 1 point repeating 9, or 1.9 repeating, I guess. So if you just add an infinite number of 9s after that, then you might be thinking, well, isn't that the number that's right before 2? So 1.9 repeating. And actually, no, that's not. That's actually the exact same thing as 2. All right. So that's kind of crazy, but it's a good thing, though. It's a good thing that's true, because if it weren't true, then that would mean that there is a number that's just before 2, a real number just before 2, which would cause a lot of problems for a lot of things in a lot of math. So if you're wondering why this is true, it's kind of a topic for another video, so we'll put that in another video maybe. But also there's a lot of resources on the internet you can check out for that. Anyway, it's kind of interesting, but again, don't think about it too hard, because it's hard to wrap your head around that if you're new to that. But anyway, so all you just have to know is that you can get as close to 2 as you want, but no matter how close you get, you can always get a little bit closer, which means your y values still get a little bit bigger. So anyway, we lost our global max here is the point. Okay, so let's look at part D. So part D is going to come as no surprise really. So for part D, let's get rid of both 1 and 2. So 1 and 2. So now we're just going to have an open interval from 1 to 2, so we don't have 1 or 2. So this is really just parts B and C combined. So here's 1, here's 2. Yeah, it's really not to scale. 2 and 4. So now we have an open circle here, right? So actually what happened here is we lost our global min and our global max, okay? So the point I'm trying to make here is that you need to have a function that's continuous on a closed interval and a bounded interval, and then if all three of those things are satisfied, then you're guaranteed to have a global min and a global max. But what we did here in example 1 is we took out the closed interval. So for part A, it was still closed, so it's okay. But for parts B, C, and D, we saw that if we don't have a closed interval anymore, we might lose the min, we might lose the max, or we might lose both, okay? It's also possible you won't lose any of them, so let's see an example like that. So we'll do example 2 real quick. So for example 2, so still the same kind of question, what if the interval isn't closed? So let's do example 2 here. So let's do, let's say we have g of x equals x cubed minus 3x. And then for part A, let's be on the interval from negative 1.5 to positive 1.5. So for part A, we'll still do a closed interval. Okay, so what do we have here? We have a continuous function on a closed and bounded interval. So that satisfies these conditions. So the extreme value theorem tells us this function has to have a global min and a global max. Okay, now if you don't know what that looks like, that's okay. You just toss into a graphing calculator, and we'll see that from negative 1.5 to 1.5, it kind of sort of looks like this. So pretty bad picture, but it's got that cubic shape, x-axis, y-axis. So x equals negative 1.5 is about here, positive 1.5 about here. Now we see that on a closed and bounded interval, this continuous function has a global min right here and a global max right here. All right. Now for part B, so what we're going to do for part B is take out this left endpoint. So for part B, we're going to have negative 1.5. Not including that now, so then up to 1.5, but still including that. So if we want to draw a picture of that, so it's still the same function, right? Still the same function, but now we're going to take out this endpoint. So this endpoint's gone, but we still have all this other stuff here. Okay. So x-axis, y-axis. So notice this endpoint is gone, but so what, right? Our global max was up here, and the global min is down here. So we still have those. Let's zoom in a bit on these. So notice if we take out the left endpoint, that doesn't affect the global max, right? Here's the global max still, here's the global min still, that's okay. Parts C and D are pretty much the same idea. So instead of making new graphs, we'll just put C and D here. So part C is going to be the same exact thing, but for part C, we'll keep the left endpoint, and we'll lose the right endpoint. Okay. So what that means is now we're going to have an open circle over here and a closed circle here. But notice the global min is still there, the global max is still there, right? Now for part D, let's take out both of the endpoints. So this is just a combination of parts B and C, so nothing new or surprising here. But now we're losing the right endpoint and the left endpoint, but notice the global max is still there and the global min is still there, right? So the point I'm trying to make here is that the extreme value theorem says if you have a continuous function on a closed and bounded interval, then you're guaranteed that the function has a global min and a global max. But if the interval is not closed, then you have no clue what could happen. You might lose the min, you might lose the max, you might lose both, or you might still have both. So we just saw examples of all of that. All right. So let's see what happens if we play around with another condition. So let's get rid of this. So this is pretty much all we're going to be doing for the rest of the video. So if you want to know about the extreme value theorem in detail, you can keep watching, but otherwise you can skip ahead to the next video. But anyway, now let's ask ourselves, what if the interval isn't bounded? So it is possible to have a closed interval that's not bounded. So what if the interval isn't bounded? So an example of a closed interval that's not bounded is this interval here, from 0 to positive infinity. So this interval that includes 0, and it goes all the way up to positive infinity. So this is a closed interval. It's not bounded, but it's still closed. Okay. So this does satisfy the definition of a closed interval. If you're curious about that, you can look up the definition, or there will be other videos on this kind of thing at some point. Currently, there aren't any on my YouTube channel, I mean. But elsewhere on YouTube, I'm sure there are videos that explain this kind of thing. But this is a closed interval, and this is the one that we'll be using here. So, if you're kind of curious, just as a quick note, this interval is closed because its complement, which is negative infinity to 0, like this, its complement is open. So this is an open interval, and if an interval is open, then its complement is closed. So these are complements of each other, so open interval, closed interval. But anyway, if you're curious about that, there are a ton of resources on the internet, and we will have our own videos about that up shortly, hopefully. Okay, so what if the interval isn't bounded? So let's see. So we'll still have a continuous function on a closed interval, but now the interval won't be bounded, all right? So this is going to be example 3. So let's say we have f of x equals 2x on 0 to positive infinity. So what does that look like? So again, remember, this is a closed interval. It's just not bounded anymore because it shoots off to infinity. So here's x-axis, y-axis. 2x is just going to look like this. So from 0 all the way up to infinity. So here we have a global min, right? Here's our global min, but there's no global max because the function just keeps shooting up off this way, right? So the function just increases, never stops increasing. So no matter how large of a value you get on the function, you can always get a larger one. So there's no global max here, all right? Now, let's see, what about, let's do another example here. So this is example 4. Example 4. Let's say we have f of x equals negative 2x on the same interval 0 to infinity. Okay. So it's a continuous function on a closed interval, but now the interval, it's not bounded, right? So let's see what happens. So negative 2x on 0 to infinity, so x-axis, y-axis, that looks like this. Okay, so here, what do we have here? We have a global max. Here's our global max, but there's no global min because the function just keeps decreasing. Okay, the function keeps decreasing and never stops decreasing. So no matter how low you go, no matter how small or no matter how negative of a value you get, you can always get another one that's that's more negative. In other words, it's less than that. So there is no minimum value because you can always find a smaller one. Okay, but you do have a global max still. So let's look at 2 more with regards to this question here. So we'll look at example 5. So example 5, example 5 is, let's say we have g of x equals 3 on 0 to infinity. Okay, so that's infinity right there, 0 to positive infinity. So what is it? It's a constant function, right? So it's still continuous. Constant functions are continuous. So we have a continuous function, x-axis, y-axis, on a closed interval, but it's not bounded. So if we want to draw this here, this is a 3 up here, and then it's just going to shoot off this way, right? So what do we have here? Well, it's a constant function. So it's a continuous function, it's constant, and it's also defined on a closed interval, but it's not bounded. But notice every point here is a global min and every point is a global max, right? Because remember, to be a global min, you have to be less than or equal to everything else. To be a global max, you have to be greater than or equal to everything else. But since this is a constant function, all the y-coordinates are the same. All the y-coordinates are 3. So every point is a global min and every point is a global max. So here, here's an example where, you know, if we lose the condition of boundedness, things are still okay. We still have mins and maxes, right? Now with example 6. Okay, so again, if you're still watching, the point I'm just trying to make here is that if you lose one of these conditions, you just don't know what could happen. And I'm just trying to show you that with a bunch of examples here. So for example 6, let's look at h of x equals x, x times the sine of x. So a pretty strange function, but anyway, that's what we're dealing with here. So x sine x on 0 to infinity. Okay, so this is kind of a strange function, but if you toss that into your calculator, you'll see that, so let's make some room here. X-axis, y-axis. Okay, so it's going to start here at 0. And then what it's going to do is increase just a little bit, and then come back down a little bit, and then increase a little more, come back down a little more, increase more still, come back down more still, increase even more, come back down more still, and then this pattern is going to keep continuing here. So as you keep going further to the right, basically what's happening is the function keeps increasing up like this. So here, there's a local max here, a local max here, a local max here, a local max here, but they keep increasing. They never stop increasing. So, you know, if you keep going farther out to the right, this function just keeps increasing up this way. Okay, it increases according to this line here. And then same thing down here, local min, local min, local min, local min. but the function keeps decreasing. Okay, no matter how far out you go, you're always going to be able to find smaller values down here, larger values up here. So actually there is no global min, and there is no global max. Okay, so this function has no global min, no global max. All right, so what do we, let's zoom out a bit and recap these examples. So what do we just see here? We just seen that, well, if the interval isn't bounded, then we might still have a global min, we might still have a global max, we might still have both, or we might have neither, right? So here, this has a min, this has a max, this has both. Example 6 has neither. Okay, so again, the point I'm trying to make is that if you want to guarantee a global min and a global max, the function has to be continuous, defined on a closed and bounded interval, and then you're guaranteed a global min and a global max. But if you play around with any of these conditions, even just one of them, then you just don't know what can happen. All right, so we have one more condition to play with here. So we already asked, what if the interval isn't closed? What if it isn't bounded? Now let's ask, what if the function isn't continuous? So we're going to have a function that's not continuous, but we'll still have a closed and bounded interval. So with this one, we won't be as specific as we were before, but let's just take a look. So let's say, what if f of x is not continuous? Okay, so that's the question we'll ask now. So example 7. So for example 7, let's just draw a picture here. So x-axis, y-axis, let's put a will be here, and then we'll start the function up here. And we'll come down like this, back up like that. We'll stop here. So here's b. Okay, so let's zoom in just a bit on that. So here's y equals f of x. Okay, so notice this is a continuous function, right? It moves continuously from a to b. It's the closed interval because we include the endpoints. It's bounded because it doesn't shoot off to infinity. So a continuous function on a closed and bounded interval. Here's our global max that we're guaranteed to have. Here's our global min that we're guaranteed to have. Now, what if we play around with this so that the function is not continuous? Well, what if we make it discontinuous over here? Okay, now the function is not continuous, but hey, look, we still have our global max, we still have our global min, so that's okay, right? Now, what if we make the function discontinuous down here? Well, uh-oh, we just lost the global min, right? So the point is, if the function is not continuous, then the discontinuity might happen where the min or the max should be. Okay, so in this case, it happened where the min should be. So let's put that back. What if we're discontinuous up here? Well, that's where the max should be. So notice, if we're discontinuous up here, we just lost the global max. Okay. So here we have our global min back over here, but if the discontinuity is up here, then we lost our global max. Okay, we lost the global max. Now, what if we have two discontinuities here? So the examples we're making here, they're kind of cheap and extremely made up. But the point is, if you don't have these conditions all satisfied, if you don't have all three of these satisfied, the point I'm trying to make here is that anything could happen, you just don't know. So here, this function is not continuous, but still closed and bounded interval, but notice the global max is gone and the global min is gone. Okay. So basically, what we just saw here was that if the function is not continuous, we still might have both the global max and the global min, like if the discontinuity is over here. We have both the max and the min, or we might lose one of them. Okay, here we lost one, or we might lose the other one up here, or we might lose both. Okay, so again, throughout this video, we've just seen a bunch of examples where even if only one of these is not satisfied, then we just don't know what could happen. We might have a global min, we might have a global max, we might have both, we might have neither, right? But as long as all three of these are satisfied, continuous function, closed interval, bounded interval, then we're guaranteed a global min and a global max. So that's pretty much the intuition for the extreme value theorem. I hope that helps with that a little bit at least. But again, a real proof of that requires some pretty advanced math, which we can't really get into here. So some calculus textbooks do kind of have a proof of that, proof so to speak, but they do rely on properties from advanced math and they kind of sweep it under the rug a bit, which is fine in some cases, but it's really something that's best to be avoided if possible. But anyway, I mean, it's just personal preference really. But here, I hope these examples give a little bit of intuition at least as to why this might have to be true here. So that's the extreme value theorem.